Okay, welcome to class 12, and this is the last class before our spring break and the last class before you have to deal with or the midterm, which is after spring break. So make sure to look at the announcement that's on the course page about the midterm and when that is for your section. That will be in person, so make sure to plan for that. Read that email, read that letter that's posted on the course page, and be prepared for that. There will be a study guide that's posted as well for that. Make sure to go through that outline and study for the midterm exam. Now, today what we're going to do, this is something that I thought about waiting until after the midterm, but I'm going to go ahead and get it in now since we lost a day due to weather. I don't want to get too far behind because there's stuff I want to get through this semester that will help you with your career and your lives. So I want to make sure we get that, have enough time to cover what we need to cover this semester in this class. So what we're going to do today is we had last class talked about the difference between processes and threads and how you have to deal with processes a little bit differently because they're completely isolated from one another. They don't share memory. By default, they don't share global variable space. They can't share object references. So we have to deal with those in a different way than we did with threads. And that means that communication between processes becomes much more important because that's the only way they can share data or cooperate with each other on some sort of task is through communication. And specifically, the kinds of communication we're going to look at today are queues, which we looked at last time, but we're also going to look at another thing called pipes and another thing called managers today. All right, so let's go and get started. So quickly as a review, we looked at threads and processes as methods of creating concurrent solutions. And as a quick review, let's look at the differences between those two. So threads versus processes. Threading, all threads share the same process space, meaning that they share memory for the code, memory for the data, any open files, or open devices. Each thread has its own execution context, meaning it has its own set of stack memory and variables. So they can have their own local variables, their own that are independent from each other, and their own set of registers that keep track of where they are and what they're doing. But in Python, there's still one Python interpreter that's managing the creation and switching managing the switches between those threads. And that's true for single-threaded solution too, but with only one thread. There's only one set of local variables on one stack with one set of registers, and there's no reason to switch. Now, with multi-processing as opposed to threads, each process has its own completely separate process space, which means that everything is independent. Memory is independent for code. Memory is independent for the data. Memory is independent for what files have been opened or devices have been opened by that process. And each process is managed by the operating system and has its own independent Python interpreter in the case of Python. So rather than having one Python interpreter with multiple threads inside of it, we have a Python interpreter in one process, another one in another process, another one in another process, and so forth. And then each of those processes could have multiple threads within it. So the takeaway from this is that processes are kind of completely isolated and independent from each other by default. So if we want them to be able to cooperate on a solution, or if they're competing with each other for some resource, they are completely separate in doing so. That means that if we want them to work together to cooperate, we need to have some sort of communication or synchronization that works across these different through these different process kind of isolation barriers. Now, as a quick overview of what we were talking about here, this would be a single-threaded process here on the left. There's the process inside the operating system with memory allocated to it for code and data and any file I/O that's being done, so files that have been opened. That also includes devices that have been opened. And then there's a single thread inside there that keeps track of the local variables on the stack and any registers or other things like that. Now, when we go to a multi-threaded approach, it's still a single process, still has this code and data up here that are shared between all the threads, still has a set of files, just like that. But now we have multiple threads that can each be running, and then the Python interpreter is going to switch between these. So it's the interpreter that's doing that switching inside of here, but it's still one process. But with a multi-processing setup, we basically have a duplicate of this, where each one has its own code. But notice the takeaway from this is that threads can easily share this data that's up here because they're all inside that one process together. But processes are isolated and independent from each other. This code and this data and these files are completely separate than this code and this data and these files are completely separate for process N over here. Now, implications from that, as a quick review, threads can share data which makes it easy for them to work cooperatively. You just make a global variable, they can all access it. Or you make a global object reference, they can all reference it. There's low overhead for creating and managing them because you're just making another thread inside of an already existing process. They have to share, however, a single interpreter. So a single interpreter is doing the switching between them. And execution, though, because it is a single interpreter, even though it can be concurrent with where each thread is, due to the global interpreter lock, which we mentioned last class, it's not truly parallel. We're not running on multiple processors. We're running on one processor, running one process, and it's switching between them. Now, that can still give us an improvement in performance with something like an IO-bound process, which we looked at previously. But we're not getting true parallel execution. Now, processes, on the other hand, since they are completely isolated and independent from each other, they can't share that data directly. That means they have to use other mechanisms to communicate and work cooperatively. There's a higher overhead for creating and managing them, again, because they each have to have their own memory allocated. The operating system has to create a process for each one, so there's more overhead associated with that. Each has an independent interpreter, but the advantage of that extra overhead and that extra work is execution can be truly parallel. This process-based concurrency can also be more easily scaled across multiple physical systems. In other words, if you look at like a Google search or the way YouTube is implemented, it's not implemented as a single computer that serves all the data for YouTube. It's an entire cluster of thousands of machines that are all working together to produce content for people. Or in the case of Google search, it's when you type in a search, it's not one computer giving you the results, it's a whole network of them. And that having separate processes where it's separate, completely isolated like this, and they can still communicate and cooperate on things, notice that because this is not sharing data within one process, you could run these on the same machine or on different machines or on a whole cluster of machines, as long as there's a way to communicate between these things that can cross machine boundaries like that. All right, so communicating between processes, there are some tremendous advantages to using processes rather than using threads. But anytime we have multiple processes, we want a cooperative solution, we need to overcome that lack of shared memory or overcome that isolation. And the way to do that, we got to have ways for them to communicate with each other, multiple processes to communicate and share data. We have to do so without directly sharing memory. So there are several options available for that. I've listed some here. We're not going to look at all of these today. Queue objects, pipes, value/array objects, manager objects, C-types, sockets. And there are other frameworks as well that help with that, like MPI, which we might have time to look at later this semester. But we're going to start looking at a couple of these today. We'll look at more later. There's also a shared memory object that we can create that uses a operating system level method for sharing memory between things. But notice it's when we do that, we're not truly sharing memory like we are with threads back here. You rather than the shared memory being part of the process, it would be outside of the processes being managed by the operating system, and then the processes are accessing that memory that's outside of the processes themselves. And we'll look at how that works in a future lecture. Now today, what we're going to do is let's do a quick review of queues. We looked at those last time, and this is a queue being used in multiprocessing. So notice that we have this process, it does some stuff, and then it eventually puts something into that shared queue. Now, how does this process get access to that shared queue when it can't have a global reference? Well, we have to pass it in as a argument or a parameter, and then we receive that shared queue reference, and then we can put things into it. If we tried to make this a global and say, put the shared queue and declare it up here, it wouldn't work, because when we make a new process, it clones the original, including all variables. We would get another thing called shared queue. We'd get a copy of that we would access. So we need to set this up so we pass in the reference to that shared object into that process when it gets created. So notice the way this works. In our main thread, we create that main queue. We pass the main queue to this process when we create it using my process. So this gets spawned as a new process. We pass the reference to that main queue into that. We put things into it here. We get things out of it once we're done down here. So this is a way to have 10 of these processes get spawned, all do their thing, put their result in that queue, and then read all 10 of those results back out down here at the end. So this is a code like where we used a queue last time. And note that you can do this passing things into processes, including object references. You can do that with other things as well for synchronization. You can pass a lock into there. You could pass a semaphore into there, or condition object into those. So note that this is how you would do that with those other objects as well. You cannot, with processes, make them globals and just access them, because there are no cross process global variables that are accessible. We have to use one of these mechanisms to do that. All right, so queues can be accessed by any of the processes that have access to the object. Multiple queue objects can be used. All entities interacting with the queue can put items in a queue or get items from a queue. And like I said, you could do that use that same technique for synchronization and communication. And we can use those other things as well. Locks, rlock, condition variables, semaphores, bounded semaphores, barriers, events. Pretty much all the things that we saw with threading we can use. We just have to, the way we access them can't be as a global reference. It has to be passed in as an argument to that process when the process gets created. All right, so to communicate between processes, this is something that's new now. So again, this was just finishing up queues, which we looked at last class. Now let's look at another method called pipes. And pipes are something that have been around in operating systems for quite a while, the concept of a pipe. And you might be familiar with using pipes on a command line interface. We'll talk about that here in a second. But the general concept is that a pipe is managed by the operating system. It gets created, and it's got two ends. It's got a read end that you pull things out of the pipe, and a write end that you put things into the pipe. So one process can then put data into the right end of the pipe, the input end. Another process can pull things out of the pipe, the read end of the pipe, which would be the output end of that pipe. Pipes are unidirectional, meaning that they're designed to be used to link one process with another process and only have data go one direction. In other words, I can't have process 2 here talk back through the pipe to process 1. So it's just a one-directional communication mechanism that process 1 can stuff data in, process 2 can pull data out, and get what process 1 sent to it. Now, as an example of where you may have seen this before, I don't know if you've done much with Linux or Unix at a command line level, or you can also do things like this in Windows as well on the command line. But most operating systems allow something like this to be done on the command line. So this is Unix, so you can say cat, the name of a file. This is just the prompt, this $sign. And then you can say this vertical bar, that means pipe the output of this process to the input of this process, and then pipe the output of that to this process here. So this is actually connecting 3 processes together and saying, okay, process 1 is cat. What does cat do? That just displays the contents of this file normally on the screen. But what we've done is say, take the contents of this file that would have gone to standard out of this one and pipe that output into the input of grep. And what grep does, it filters the input stream that comes into it for a specified pattern. In this case, my last name, Yost. And then we could pipe that with WC, which is a word count program that's counting the number of lines. And then the output of that just goes to the console because we didn't pipe it somewhere else. But this is a really cool feature that Unix had implemented many years ago, back in the early 70s, that allows you to have complicated results come from just running multiple processes and having this simple communication between them. So this, for example, would count the number of times, the number of lines that Yoast appears on in file.txt. So if I were to take the class schedule for next semester, or the fall, or this semester, and call it file.txt and run this command line, it would give me the number of classes I'm teaching and the number of times my name is associated with a class. Or we could use it to account the number of lines that have Monday classes by putting like Monday or whatever in here. That's how many Monday classes there are that are in the list. So it allows you to do things that would otherwise require programming all on a command line by just hooking utility, the output of one to the input of another, output of one to the input of another. So the command line interpreter, the command interpreter starts the programs in separate processes. It creates the pipes that link the output of one to the input of the next, and then executes all of them. So again, here's what that looks like from the process point of view. Standard in hasn't been reassigned, but out gets piped to in. Out of grep gets piped to in of word count -L, WC TAC L, and the output of that just goes to the console. So that also makes it so these programs themselves at the operating system level don't have to be designed to know how to read from a pipe. They just have to read from standard in, and they just have to write to standard out. And those can be plumbed or connected to other processes. It's a very, very clever. It's a brilliant way of setting up an operating system so that you can have complicated things like this without having to change the code to talk to different programs or know how to talk to those different programs. So programs don't even have to know that they are talking to each other, because this is just saying, hey, whatever I get as input, I filter it for that, and I output my output, the ones that match, the lines that match that, I pass on. And this just says, hey, anything that comes in, I'm going to count the number of lines there are in that, and I'm going to output that to my standard out. Very clever, absolutely brilliant. Okay, so pipes exist in operating systems, Linux, Windows, Mac, other operating systems implement that as well. And the OS can manage those. We can also create our own and manage them in code. So just like on the command line back here, we let the operating system create those and link them up. We can also write code that does that ourselves. And the easiest way to do that in Python, in a cross-platform way anyway, is using multiprocessing.pipe, which creates one of these pipe objects. So that creates an object that's similar to a typical operating system pipe. The only difference between the Python multiprocessing.pipe and standard pipes at the operating system level is that Python pipes are duplex by default, meaning that both ends can read and write through to the other end. So they're kind of two-directional. And essentially what happens is when you make one of those pipe objects, when you make an instance, it returns two connection objects, connection 1 and connection 2. In operating system pipes like in Unix, it has a read end, or a write end and a read end. In this, it just has two connection objects. And those connection objects are what we're going to use to talk to the pipe through, as we'll see in a second, but it returns a pair of them, again, representing the ends of the pipe. There's also a parameter, it's duplex equal true. You could say duplex equal false, and then connection 1 would receive, connection 2 would send. So this would be the read end, that would be the write end, if you set connection to false, or duplex to false. All right, probably the easiest way is to look at an example program here. And for the record, I don't know why I'm importing time or random, because I don't think I'm using those anywhere. But anyway, I'll just leave it there. It's probably left over from another program that I had this developed from. But notice here, this is a classic producer. In this case, it's just producing these messages. You could imagine somebody's typing those in to produce them rather than having them just produced here. Oh, I am using time and sleep and random right there. So that's why. So I'm waiting a random amount of time between this simulating somebody typing in messages. So this pipe.send, it's the first time it's going to send hello, and then between 1 and 2 seconds later, it's going to say, are you there? And between 1 and 2 seconds later, it's going to say, hey, lol, okay, thanks, bye, end. But notice that it going through there, it's going one message at a time, sticking them into that pipe. And you'll notice that I passed the pipe into this producer as a parameter, just like we had mentioned earlier with queues. Same thing we're doing here. Now consumer, we're passing the pipe into it as well. And really, I'm calling this pipe, but really maybe it's a pipe connection, I suppose. This is one connection is going into producer, one's going into consumer. And you'll notice that here we create the pipe. Pipecon 1, pipecon 2, that creates the two connection ends. That's the two ends of the one pipe that was created. And we're passing one end to the producer, the other end to the consumer. And then we do p1.start, p2.start, p1.join, p2.join. So we're starting the processes and joining them, then printing done. So essentially what this is going to do is we now have two processes that are completely isolated and separate from one another. And what we have is we're passing in, the producer is sending messages to the consumer who's consuming them and just printing them out on the display here. Now, you'll notice that this pipe is allowing us to send messages from one, have them received on the other. Now, we could also have done this with queue. So what's the advantage of using a pipe here? So let's look at what the difference is. Pipes only allow two endpoints. We can have a write end and a read end, or you can say connection 1, connection 2. By default, they allow duplex communication, meaning it can be two-directional in Python, but they're not safe if we're going to use them with more than one process reading or writing to the same connection. In other words, they're only designed to be point to point. So in other words, if I have two processes that go to communicate, and I want this one to talk to this one, a pipe is the way to do that, or is a way to do that. On the other hand, if you have multiple producers and multiple consumers, then you want to use a queue. So you wouldn't use a pipe to gather the results from dozens of different programs that are running, putting things into the queue. They're only designed to be have one pair of endpoints, two endpoints. So peer to peer. Now, another thing about queues is because they allow multiple producers and consumers, they do that safely. So any number of processes can read, any number of processes can write. They can emulate a pipe by only using one writer and one reader process. It essentially works the same way at that point. But pipes are faster. because they can be built directly on top of the pipes that are implemented within the operating system itself. And note that we could even use the operating system pipes directly. It's a little less portable, but you could actually do this. You could say import OS, and then you could say os.pipe, and that produces a read end and a write end of a pipe. So you could do this directly, and we're using an operating system pipe directly. It's considered more portable to just do multiprocessing.pipe because it's all been abstracted and implemented behind the scenes however that operating system needs to. Oop, we went a little too far ahead there. So you can do this, but I would recommend just using multiprocessing.pipe. Now, the third and final thing that we're going to talk about today is the concept of what's called a manager. And a manager is a special object that's part of multiprocessing, and it acts as a guard and guarantees thread-safe, process-safe access to some kind of data and objects that we associate with that manager. So it's similar to the monitor concept we talked about earlier in class 3 or 4, whenever that was. But the difference here is that we don't have to implement that ourselves with our own synchronization mechanisms and our own passing those synchronization mechanisms or condition objects or whatever to those things. The manager handles all of that internally for us. It handles a lot of the implementation, so we don't have to. And you can use a manager with threads. You could also use a manager or with processes. You could also use a manager with a process that has multiple threads running inside of it. So it's kind of both process safe and thread safe. So managers support the use of namespaces, and those can help us organize the protected data into kind of these subgroups of synchronized protected things if we want to. So the idea here is we would create a namespace, and then once we've created that namespace, we can add data items to it. So this is also a little bit different than what we had earlier with that monitor concept, in that this is something that you can create kind of a manager, give it a name, and then you can associate whatever data you want with that dynamically. So you can say, add this data to this manager, add this piece of data to this manager, add this one, and then all of those different processes can then access that data has been associated with that manager or in that namespace. All right, so adding attributes to a namespace is pretty easy. You just do it by assigning a variable, but you do that by using the namespace first. So kind of like you would a module, just like you'd have like random.randint or something like that. We create a namespace, and let's back up a second and look at how you do that. So you create a manager using multiprocessing.manager, and then with that manager, we say create a new namespace and call it this. So now we can just access this my namespace object, and that is going to access that namespace within this manager. It's going to synchronize everything. So we can say my namespace.count. So this could be, for example, like shared variables.count. This could be shared variables.itemList. And you just create those items in there. Once that namespace has been created and we've added the items to it, we can pass the reference for that namespace to the processes that need to access it. And since each process can then access the attributes inside that namespace, all the data items are effectively shared in a thread-safe, process-safe manner for all the items that we stuck into that namespace. Let's look at a more complete example here. Okay, so here's an example. We have this enter process. We have the exit process. This is a lot like a process version of that ornamental garden problem that we looked at earlier. So we're going through and repeating 10 times somebody entering, so we're adding to the count, and we are then decrementing that count 10 times as well. So this should be a 0 at the end. Now notice we're not putting a lock around this here. We don't have to, because it's handled by this namespace itself. So let's look at the namespace. So we created a manager, we used the manager and created a namespace within that. And now we've added the count variable to that, and we've added this log list to that. And then we start up the two processes. We pass the namespace to them so they can each access it. Notice again, it's not a global variable. It's a local inside of only the created main, but it passes it to those. P1.start, P2.start, we join both of them, and then we print out the count at the end. So at the end, the count is 0, but something strange happens here. The log ends up being empty, but we've tried to log namespace.log.append. We've tried to have entered, so we should have seen entered 10 times, left 10 times in there. And again, the synchronization is all handled by the manager for this namespace automatically. So the question here is, why did count end up at 0? That has a value. And actually, if we change this to 20 instead of 10, the count would end up as 10. But the question is, why is nothing in the log? Why is the log empty? And the answer to that comes down to more how Python works and how then that namespace thing not working properly. And the problem here is the manager, any objects that are contained within the manager are unable to propagate changes made to mutable objects inside of that container. In other words, if you have a mutable object like a list, which is mutable, where you can add things to it, take things away from it, modify it, that doesn't change the reference of the list itself. So the list itself has a reference, like an ID. In Python, every object has an ID. That ID is not changing. So the manager does not know how to propagate those changes unless it sees those things, can see that change in some way. So in other words, if you have a normal mutable Python list, then any changes are not going to be propagated because the manager has no way of detecting that things have changed inside of that because the reference hasn't changed. And as a quick way to illustrate this, since that might be unclear, especially if you haven't programmed much in Python, let me bring up a Python shell and kind of try to show you what I'm talking about here. Okay, let me switch so you can see this Python shell I brought up. Okay, so here's a Python shell. This was Python 3.8. But if I were to make, for example, a variable like x and say equal 10, that x is an integer type, but it also has an ID, and that's its ID number. That's a unique ID associated with that particular object. So with that particular object, if I were to change x to 20, change the x variable to now be 20, and I were to look at the ID of it again, notice that the ID has changed. This number does not match that one. It's a different number. It was 31936, now it's 32096. So the ID has changed. And the reason it's changed is because that's a mutable object, or an immutable object. Integers are immutable, so what I'm actually doing here, when I create this 20, I'm creating a new integer object, and I'm having x be the reference to that new object. But notice what happens with a list. We'll say list 1. That's an empty list. Let's look at the ID of it. Well, first off, what's the type of it? Type of list 1. It's a list. What's the ID of it? There's the ID of list 1, 59660424. But now let's change list 1. Let's add something to it. Let's say list1.append. And we'll just append a string to it. So now list 1 looks like this. And now let's look at the ID for it. Notice the ID did not change. And so the problem that we're having in that code is, and that's because a list is a mutable object. We can change it without changing its reference. This reference has stayed the same even though we've changed the list. And so that's what the that's what the manager object uses to know when to propagate the change from one thing to another thing. If it sees that the reference hasn't changed, it doesn't propagate any changes. It doesn't think there aren't, it doesn't know about them. it doesn't, and just like with that list that we had there, not changing, I could add all kinds of things to this and change it. So list one dot append test, list one dot append 10, and now list one looks like this. But if I do, what's the ID of list one? Stays the same, doesn't change. So the problem that we're having here is we need a way to let the manager know, hey, that object has changed, even though the ID hasn't. So let's go back to the presentation and look at how we can fix that. Okay, so the problem here was that in order to propagate those changes, we need to tell the manager somehow that that thing is something that can be changed. And it turns out that there's a manager.list type that we can use that works just like a normal mutable Python list, but the manager can update those things. And note that that's going to be true for other mutable objects as well, such as dictionaries. A mutable object type such as strings and numbers, so strings, integers, floating point numbers, we don't have to worry about that because they're immutable. If it's an immutable object type, tuples as well, we don't have to worry about it. If it's mutable, like a list or a dictionary, then we have to declare those as a special manager.list type. All right, so here's an example that actually fixed the problem. So rather than creating that myspace.log as just an empty list, a Python list, we say make it a myManager. So that was a manager.list. That creates a special kind of list that the manager can then know updates. There's some other ways to fix that are a little bit that I've seen used as well. For example, let me just switch back to Python and I'll show you something. As long as you're changing that object reference, that thing can be tracked, but that gets a little bit squirrely in how you do that, and I'll show you what I mean. So for example, if I want this list to change its ID, but not change the contents of this, I could do this. I can say list1 equal list1 and do a slice across that whole list. And I believe that this should, notice that the ID now changed. So what you could do is in your code, you could append something to that list and then take that list and create a new list formed from slicing from the beginning to the end of that one. And that would create a whole new ID, and then the manager would know to propagate the changes. But that is, especially when you get to large lists, you're spending a lot of effort recreating an entire new list in memory, making a copy of the original one over to here, which is going to change the ID, which is then going to propagate the entire change, and that can be performance-wise costly. So it's better to use the kind of built-in ability to handle that, which we can do just by saying that. And then the rest of this works the same as we don't have to change how this works. This all works the same as it did. We just had to change that to a managed list type like we did up here. And now when we run this, we get count of 0, and you can see entered, entered, entered left, entered left, entered left, entered left. And these won't always necessarily go in alternating order like they show up here. Sometimes when you run this, you'll get a different order. Okay, so let me switch back to where I can see that. So that's all for today. Everybody stay safe. That was a fairly brief introduction to 3 inter-process communication mechanisms, one of which we saw last time, queue. But we also today looked at pipes, which are kind of a more limited version of a queue, but could also perform better because they can be built directly on top of the operating system. And then the last thing we looked at were managers. And managers are actually pretty powerful because they allow us to create a block of shared data that we want shared between all these different processes. And we don't have to worry about communicating that. We don't have to worry about updating that. We don't have to worry about synchronization between those to keep them safe, because it's all happening inside of that manager object itself. And then we can have different namespaces inside of there as well. So you could have like global variables.count. You could have settings dot something. You could have return results dot something. So you can define different namespaces all within that one manager. And the defining characteristic of that manager is it shares that data, propagates the changes, and it also manages the synchronization to make sure that only one change at a time, even across multiple processes, is happening. So fairly powerful tool for use in this inter-process communication that we're talking about today. All right, so that's it. Everybody stay safe, study for the midterm, look at that review guide. Like I said in the letter, next class we're going to have kind of study time, review time, make sure everybody has their labs working, and then 1 week from today you'll have your midterm exam. It'll be in person in the classroom. So be prepared for that. If you have any questions over spring break that come up, or things that you're working on and you want help with them, or things when you're looking at the study guide that you don't remember, don't understand, or that are a little bit hazy, ask me. Even over spring break, I'll be around to answer questions. So don't be shy about sending me a text message or sending me an email, or if you need to, setting up a Zoom chat or a phone call. Or even if you need to meet face-to-face, I'm happy even over spring break to come and safely meet with you. But that's it for today. And have a good spring break, and I'll see you guys all shortly. Should get out and enjoy the weather while it's nice too.